Welcome to Lesson 10C, Quantitative Analysis of Fanno-flow. In this lesson, we'll close the loop on solving Fanno-flow problems by applying the Moody chart, or actually the Churchill equation, which we can use to generate the Moody chart. And we'll look at how to use the critical or sonic state as a reference in Fanno-flow. And as we've seen previously in other kinds of flows, we can use this reference value at the sonic state even if the flow is not choked. In other words, even if this state never exists in the flow. And finally, I'll show you how to use the CAC for Fanno-flow. Here's a quick review of the control volume setup for Fanno-flow through a pipe or duct, where we have this control volume from 1 to 2 with length L. And this is not to scale because this is typically a very long pipe. With friction force F friction to the left as sketched, it's the friction of the wall acting on the gas. And we have our conservation laws of mass, energy, and momentum. And we'll often need other equations like ideal gas law and thermodynamics equations, etc. I list some of them here. Let's evaluate this term in the momentum equation. Well, F friction over A would be the integral from x1 to x2 of tau W, the shear stress at the wall, times the perimeter of the pipe or duct, dx, divided by A, where A is the cross-sectional area of the pipe or duct. Well, this is a constant diameter or constant dimension duct, so this perimeter is a constant and can come outside the integral. So our equation reduces to this, which I'll call equation 4. So now we're left with how to find this shear stress tau W. Well, you should recall from your undergraduate fluids class the Darcy friction factor, lowercase f, where f is defined as 8 tau W over rho v squared. It's a non-dimensional parameter, and to get tau W, we just solve this equation for tau W. We get f over 8 rho v squared. So now we need to get the Darcy friction factor F for our given problem conditions. Let me sidetrack briefly and discuss the hydraulic diameter, which we'll call dH. dH is defined as 4A over the perimeter, and we use this for non-round pipes. It's a little more complicated than this, but basically we can use dH in place of d, the pipe diameter, of an equivalent round pipe. So you may have a condition where your actual pipe or duct is, say, rectangular, and we can use this equation to get the equivalent diameter or the hydraulic diameter such that the flow behaves the same as a round pipe of diameter dH. And the reason we do this is that our equations are derived for round pipes. And I'll comment here that for round pipes, if you analyze this equation, dH is equal to the actual diameter of the pipe. So we will use the hydraulic diameter and pretend that we have a round pipe, even if our actual duct is not round. So going back to equation 4 then, F friction over A equal the perimeter, which for our equivalent round pipe is just pi dH, and the area is pi dH squared over 4. The cross-sectional area. And then we had our integral from x1 to x2 in our control volume, f over 8 rho v squared dx, where this is our equation for tau W. Thus, F friction over A is 1 over 2 dH, integral x1 to x2 f rho v squared dx, after some simplification, and I'll call this equation 5. Well, it still remains that we need to find F, the Darcy friction factor. So we get F from the famous Moody chart, or there's actually a nice equation called the Churchill equation, which we can use in place of the Moody chart and not have to read off the Moody chart. Here I show the empirical equation called the Churchill equation that we'll actually use in this course to calculate F so that we don't have to read off the Moody chart. And this is how you may remember the Darcy friction factor. But don't confuse this H with specific enthalpy. You may recall from your undergraduate fluids class that the Moody chart plots F Darcy friction factor as a function of Reynolds number, and the Moody chart has a laminar portion, kind of a fuzzy transitional area, and then a turbulent portion. We define epsilon as an average roughness height, and this lower curve here is the smooth case for epsilon equals 0. For other epsilons, the Moody chart looks something like this, where epsilon increases as you move up. We'll define Reynolds number here as rho v dh over mu.
Sir, is Reynolds number still constant like it is for incompressible pipe flow?
No, BJ, but remember one of our equations from conservation of mass for Fanno-flow is that rho v is a constant. dH is also a constant, so Reynolds number depends on mu. Mu in turn depends on temperature, so as we go down the pipe, the temperature changes, and therefore mu changes, and therefore Reynolds number changes. So it's not constant anymore.
Thank you, sir.
But for the kind of compressible high-speed flows that we're talking about with Fanno-flow, Reynolds number is big, so we're definitely in the turbulent region. Even more important is that if Reynolds number is high enough, these Darcy friction factors level off after a certain Reynolds number so that they become constant, independent of Reynolds number, but dependent only on roughness. We can define some region here where to the right at high enough Reynolds number, depending on epsilon, we call the flow fully rough. So even though our Reynolds number is changing down the pipe, it's changing typically in this fully rough zone, so F doesn't change with Reynolds number. Here is an actual Moody chart taken from my fluid mechanics textbook, where we have Darcy friction factor as a function of Reynolds number and epsilon over d. Just keep in mind that we're using epsilon over dh instead of epsilon over d, and our Reynolds number is also defined in terms of the hydraulic diameter dh. But you can clearly see this fully rough zone. For example, if relative roughness epsilon over dh is, say, 0.002, this curve is almost completely flat for high Reynolds numbers, like 10 to the 7th. So if our Fanno flows have high Reynolds numbers, setting F equal constant is quite a reasonable approximation. This is a nice simplification that's actually quite accurate for these high-speed flows, that F, which is normally a function of Reynolds number and roughness over hydraulic diameter, when the flow is fully rough, Reynolds number drops out. So F is a function of this non-dimensional roughness only. This will be key to helping us analyze Fanno flows. Well, in that case, equation 5 can be simplified for constant F, so we can move F outside the integral. So F friction over A is F over 2dh, and then the integral x1 to x2 of rho v squared dx. And with this, our equation 3, the momentum equation, simplifies to P1 plus rho 1 v1 squared equal P2 plus rho 2 v2 squared plus F friction over A, and I'll use the right-hand side here. So this is now our momentum equation for Fanno flow. We can do a further analysis of this equation if we introduce Mach number and write V in terms of Mach number, and A, of course, is a function of temperature, and use our ideal gas relations. It turns out that we can do this integral. I'll draw a long squiggly arrow, which means manipulate, or lots of algebra, which I do not show. I suggest you try this on a cold, rainy night when you have nothing better to do. But it turns out that we can write this equation as f x2 minus x1 over dh equal negative 1 over gamma m squared minus gamma plus 1 over 2 gamma natural log of m squared over 1 plus gamma minus 1 over 2 m squared. And the limits of calculation here are from m1 to m2. And this equation I'll call equation 6. And I'll comment here, equation 6 holds between any two x locations along the pipe, namely x1 and x2, where we move along the Fanno curve as we've discussed previously. So let's do the same kind of trick that we did with Rayleigh flow. Namely, we'll use the star, asterisk, critical or sonic conditions as a reference state, even if the flow is not choked. In other words, even if we never reach choked conditions from 1 to 2. We can use the critical conditions, whether they actually exist in the flow or not. So for example, consider a pipe with state 1 at x1, flow from left to right as usual, and let's suppose that this is the actual pipe exit, which is our state 2. Well, we'll imagine an extension of this pipe to a new imaginary exit where we have star conditions, sonic or critical, at this imaginary exit. So this location is x2, and this we can call x star. We'll let L be the actual length of the pipe as we've used previously, but we'll define L star, and I'll call it L star 1 to show that we're starting at location 1. This pipe could extend farther upstream, so we're going to indicate L star 1 as the length required to reach sonic conditions or critical conditions starting at state 1 or x1. This L star 1 is the maximum pipe length starting at 1, and that's the location at which the Fanno-flow chokes. In other words, Mach number is 1 at this critical state if we extend the pipe to L star 1 as I show here. Now let's return to equation 6 and imagine that we have this extension with total pipe length L1 star. What we'll do is let x2 minus x1 equal the maximum pipe length L1 star where we get critical conditions. We'll also let M2 in that equation equal 1, since what we're doing is setting state 2 to the critical conditions, where Mach number is 1. Well, after some algebra again, which doesn't require such a cold rainy night, we get FL1 star over DH equal 1 minus M1 squared over gamma M1 squared plus gamma plus 1 over 2 gamma, natural log of gamma plus 1 times M1 squared over 2 plus gamma minus 1 M1 squared. And I'll call that equation 7. Well, finally, we'll make this a little more general, namely starting at any x location, not necessarily state 1. Let's copy and paste this equation here, but get rid of all these 1 subscripts and call this equation 8. I'll put lots of stars here, and I'll call this our Fanno-flow workhorse equation. We'll be able to apply equation 8 starting at any x location along the pipe. It turns out that equation 8, our workhorse equation, is what's tabulated in Fanno-flow tables and in the compressible aerodynamics calculator online. I'll show you how to use the CAC for some example. Let's take m equals 0.3 with air as our gas. I plug this and this into equation 8, and without showing all my numbers, you can verify that this gives FL star over DH equal 5.2993. Now let's check this result with the online compressible aerodynamics calculator. We've already talked about isentropic flow, normal shock relations, and Rayleigh flow, but right above Rayleigh flow is Fanno-flow. The default for gamma is 1.4, so we'll leave that alone, but we'll change this default 1.0 to 0.3 for the Mach number and calculate. And you can see that we get our same 5.2993 value for this FL star over D. But notice something peculiar here. There's a factor of 4 that we don't have in our equations. So the CAC tells us that 4 FL star over D is 5.2993. So what's the deal with this factor 4? Well, it turns out that the good folks who generated the CAC defined the Darcy friction factor differently than we do with this factor of 4. But that 4 kind of goes along for the ride, and this means the same thing as our term here. and you could verify that by getting the same answer. So for all practical purposes, we can ignore this 4 in the CAC and just use it to mean this collection of terms in our equation 8. And they do agree, which makes me happy. In other words, 4F L star over D in the compressible aerodynamics calculator is the same as our F L star over DH. So as long as you remember that and don't do something with that 4 like divide it out, you can use the compressible aerodynamics calculator. What about at supersonic Mach number when we're on the lower branch of the Fanno curve? For example, try m equal 2. Equation 8 still works. It gives F L star over DH is about 0.305. And on the CAC, if we change this Mach number to 2.0 and calculate, we get our 0.305. But I wanted to point out that for subsonic flow, this is fairly long compared to supersonic flow. In other words, supersonic Fanno flow reaches the critical condition in a shorter pipe length compared to subsonic flow. And a final comment, if you make the actual L greater than L star, the upstream conditions must change, just as they did with Rayleigh flow. For the subsonic case, conditions 1 will change, and for the supersonic case, you'll get a normal shock somewhere upstream, so the whole flow changes to subsonic. In the next lesson, I'll show a procedure for how to solve Fanno-flow problems, and we'll do an example. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.